which one is the correct cable. Let's see. Where? What? This one's correct. Getting things out. Okay, finally. So this is okay, and this one, wait. So this one I need to go here first, and PPTX. There should be a slideshow. Where? Huh? Annoying. PowerPoint slideshow. Okay. Okay, finally everything set up. So any question? From last time we are going over. Okay, so we are going everything into abstract version. I think this is, I don't know, at least for me, is probably the most interesting part of the course now. So now we have the abstract version of the inner product space. So we are talking about all the inner product and goal orthogonality. Okay, so for this 5.4 is a start. So chapter 5 we are talking about those orthogonality things, and so remember we start chapter 5.123. I guess only 1, 2 we are talking about orthogonality in the inner product in Rn. So in Rn, inner product has a very very simple definition. It's like inner product between x and y with coefficient ai and bi, and it will be okay. So maybe it will be here. No, okay. Anyway, so let's use this. Although it's different. Okay, so no, it's more confusing. Okay. Anyway. So for things in Rn, then the inner product is very simple. It's like x has coefficient ai, y has coefficient bi, then the inner product is just some ai times bi. Okay. So in Rn, then we have the inner product equal to some ai bi, where ai is the coefficient for x and bi is the coefficient for b. No, not coefficient, coordinate. Okay. And but then okay, so those are in Rn, and we have inner product, and we convince ourselves that in Rn inner product has a relationship to the structure of to the geometric structure of vectors. So we have like a non-square. So we have the length of your vector square. Wait, how do you actually write vector? Maybe this. Length of your vector square equal to the inner product of the vector with itself. This we kind of convince ourselves in Rn, or more like we convince ourselves in R2 and R3, because in R2 and R3 we think, say in R2 then this thing is x1 squared plus x2 squared, and by the Pythagorean rule we think that's the length of the vector x squared, so like this thing. In R2, then this is x1, this is x2, so the length of x squared should be x1 squared plus x2 squared. And in R3, we think that's a similar thing, and we believe this is generalized for Rn. Okay. And also we have the cosine rule, and we say the inner product basically tells us the cosine theta between those two vectors. So say if this is both of them are length 1, so we have a unit vector because we know length now. So we can normalize our vector to unit vector, and then we say we have a unit vector u and a v. Then the inner product between u and the v will be equal to cosine theta. Okay, so those were all the things we derive in Rn, and then now we go to abstract space, and we say that we have an abstract inner product that just satisfies those 3 rules, just like what do they satisfy in Rn. These inner product in Rn satisfy. then we think we can define all the geometric structure of of your space just like in Rn. So we can define the length of a vector square from inner product by just doing this length square equal to inner product with yourself, and also we prove abstract version of the Cauchy-Schwarz inequality. So we see that the inner product between the two vectors also proportional to, you can design some. Okay, so it's kind of reverse, because in abstract space we don't have like a natural theta that's just like in Rn, but we see that we still have the Cauchy-Schwarz inequality for the inner product of two vectors, and so we kind of do it in the reverse. So because of this, we think that we can also define angle theta between two vectors by thinking about inner product between two unit vectors is cosine theta. Okay, and another thing that will be very useful today we didn't say is also that we have so we think two vector y x and y are perpendicular, means that their inner product is 0. Okay, this kind of come from this cosine theta. So if you have two things that's orthogonal, then x and y orthogonal, then cosine theta equals 0, so their inner product equals 0. Okay. Yeah. So we define all those geometry. We show that the inner product gives us all those geometrical structure. We have the length, we have the angle theta, we have the orthogonal. I guess I should say orthogonal before the theta. Anyway, we have the orthogonal and the theta all defined by inner product, and so those can be verified in R2 and R3 because we have all those concepts in R2 and R3. Then we think we can generalize to Rn, and we think we can also generalize to general inner product space, where we have abstract linear space and abstract inner product defined. This abstract inner product is this abstract inner product is just a function that you take two vectors and you need to satisfy those three properties. Okay? And once again, the three property, first one is the one you need for inner product to give you a norm. So inner product of a vector with itself must be greater or equal to 0, and actually most of the time it's greater than 0, strictly greater than 0. So it equals to 0 only when your x is a 0 vector, and and the inner product needs to be symmetric between its two entries. So x inner product with y need to equal to y inner product with x, and and inner product is linear in its first argument. So if alpha x plus beta y inner product with z, that's alpha x inner product with z and beta y inner product with z. So you kind of have this distributed rule when you do inner product. And if you combine 2 and 3, you see that inner product is also linear in second argument. So if you have z inner product with alpha x and beta y, then it's also like this. Okay. Okay, so that's all about inner product, and then we go a little digression. Then we also talk about known space. So this is a linear space. Okay, so inner product. So yeah, so we are kind of going backward. So inner product is actually a stronger structure than a known space. Okay, so because in inner product space you always have a known that defined by square root of this x inner product with x. Okay. But there is a more relaxed notion of known space where it says that your space has a known defined on it. Okay, and the known need to satisfy those properties that we think known should have. So the known of every vector should be greater or equal to 0 if and equal to 0 if only if your vector is 0. So this is about So I guess the difference between known and the inner product is that the inner product gives you an angle, right? So inner product can tell us that two vectors has some angle, but known only tells about how long this vector is. So known on vector space tells you that for every vector we find its length, but it doesn't tell you that the two vectors what's their angle. Okay? So this is a weaker requirement on your vector space. You just say you can define a length of every vector on it. Okay, and the length should respect some linear thing. Okay, so to be a length, so we think length should be a positive number. So and your length is 0 if you are actually 0. And then the next property is we want this length to respect your linear space. So it should be linear, and that means that say if you stretch your vector to twice the length, then your norm should be twice, etc. And then if you have minus sign, so if you flip your vector to negative, then you should not change your length. Okay, so you have absolute value of alpha here. And then length, we say we don't know the angle between them, but we still want something more than just having length. So we think the length should satisfy triangle inequality. So it means that you have a 3 vector look kind of like this. Okay. You have a 3 vector kind of like this. Then so kind of like a triangle. Then we think like length of this triangle. Length of the third edge of the triangle should be less than the length of the other 2 edges of the triangle adding together. Okay, so this length should be less than this length plus this length. So that's a triangle inequality. Okay, and so you can prove yourself that if you have inner product, then because it is a stronger structure, then a norm defined by the inner product will already satisfy those. But then we see that you can. So even on a space that already have inner structure, inner product, you can define other norms. Okay, so we see that there are other norms, L1, L2, and infinite. They are not necessarily associated with some inner product, but yeah. So they are not really coming from some inner product, but they are still non-structure. So L2 norm is actually the inner product norm by how we define it, but there are also L1 norm and the infinite norm, and it's nice to know that they exist. Okay, so that's about inner product. Okay, and okay, so guys, there's a quick review for 5.4 in question, and let's go a little digression right now. So we have been talking this whole course and in a way such that the coefficients are real. Okay? So everything, so the AI and BI are real. Okay? So let's go a little outside of it. Let's think about what happens when the coefficients are not real. Okay? So we can also think about when the coordinate, coefficient or coordinate, if they are not real number, if they are complex number, okay. So most of the thing will be actually a sense of like you can still do Gaussian elimination, etc. But and yeah, so like I believe like the first 3 chapters of the course doesn't change if you just change a real number to a complex number. But this thing now change. Okay. Now if you think about inner product, then complex number and the real number are very different. Okay, it's because of this. Okay, so if you want a length of a complex number, then complex vector. So first we think about what's the length of a complex number. So complex number can be written as a real part and the imaginary part, and so just the absolute value of the complex number itself is kind of like a length. So it's square root alpha squared plus beta squared, and it's a square root of a complex number. So, but what's important here is the absolute value of this complex number is not square root of is square. It's square root of is alpha times the complex conjugate of alpha. Probably, I don't know how many of you know complex number. A lot or no? I guess raise your hand if you know complex number, and raise your hand if you don't. Okay, so I guess it's 1 versus 0, so 100% of you know complex number. Okay, but anyway, let's assume that I think you should have done this in calculus, so hopefully you already passed calculus. and yeah, so I guess drawing a picture hopefully help you remember. So complex number usually you draw like in complex plane. So it's on AI, A plus BI, okay? So you have like a real axis and an imaginary axis, and you say complex number have the real part and imaginary part, and is A, so A part real and B part imaginary, and yeah, and it's a non-square kind of thing like a two-dimensional vector. So its length is A squared plus B squared. Okay, and but it can also be written as the square root of this alpha times alpha complex conjugate, where alpha complex conjugate is this vector. Okay, so alpha is here, and you have alpha complex conjugate here, and yeah, for reasons alpha times alpha conjugate, so this is A minus bi. Okay, this thing you multiply together, and yeah, so you do this algebra here, then you see it's alpha squared minus bi squared. But I squared equal to -1, so this minus b squared b squared I squared actually become plus b squared. Okay, so that's the length of just one complex number. Okay, and okay, and now if you have a vector that has coefficients that are all complex, then what should happen? Then we think it's a length square. Its length should still be all those complex coefficients squared and taking a square root. Okay, and okay, yeah. So it should be something greater or equal to 0. So we think a length should still be a real number, and it should still be greater or equal to 0. So like this thing. Okay, we still want this property. And so we still want this property, then yeah, so we take all the coefficients absolute value squared, and adding them together taking square root seems like a good generalization of the norm of a real vector. And but now weird thing happen. So then each of those is zi, so this is z1 absolute value squared, z2 absolute squared, and zn absolute squared. Those are not z1 squared and z2 squared. Those are actually complex conjugate of z1 times z1, and it is a complex conjugate of z2 times z2, right? So you have those bar here. So it's z1 bar times z1, z2 bar times z2, and zn bar times zn. And those adding together taking square root. Okay. Okay. And so if you think about this writing as a vector, then this is z vector. Okay. Okay, so you can write this as a z vector, then times another vector. That's not z, that's a z bar vector. Okay, okay. So it's like this z bar transpose vector times this z vector, and we now have this extra bar here because we have the bar here. Okay, so the z1 bar, z2 bar, and zn bar. Okay. So this is not z transpose times z anymore. This is z bar transpose times z. Okay, so it's different. Okay, and yeah. So if we write this bar and transpose two things together as h, then we can say z bar transpose equals zh. Then the norm is then the norm of your vector is actually z to the h times z. Okay, so instead of doing just transpose, you need to do transpose and the complex conjugate to calculate your norm. Okay, and if you think about your norm look like this, then you think your inner product should also look like this. Okay, okay, and yeah, and so you see that so this should be. So you think about if this norm is defined by the inner product, then this should like z and z, right? So you see that your z and z is z bar transpose and times z. Yeah. Okay. So now it's a little different because you have the extra complex conjugate here. Okay. And so if you define inner product this way, okay. And so I think we can define our inner product between two things, z and w. We're like, so we think about z. Okay. So we think about the inner product between Z and W. So we think Z and W is like W transpose conjugate times Z in like Cn. Okay, and so you think about this thing, then it's still different because so it still satisfies that it gives us a norm because that's how we derive it, but but then the symmetry is broken between Z and W because W has complex conjugate. Okay, and so if you switch between Z and W, then you actually get a complex conjugate because so WZ will be about the complex conjugate and W, and so maybe it's easier to write this equation, right? And so this thing W conjugate and Z, so this is W1 bar. This thing is W1 bar Z1 plus W2 bar Z2 plus dot dot dot, and this is Z complex conjugate, and W is W1 Z1 bar plus W2 Z2 bar plus dot dot dot. So you see that you are barring different variable. Okay, so you have W1 bar Z1 here, and you have W1 Z1 bar here. So those two things are actually complex conjugate to each other, and they are not necessarily the same. So you have this equation here. Okay, so yeah, so you don't have this total symmetry on two argument anymore. That's the most different thing on complex inner product. Okay, and so but here we have the anyway. So let's keep talking about this first. And the third one, okay. And the third one is the linearity. So linearity depends on a bit about how we define it. But I still want the first, we still want the first argument to be linear, and is satisfied by our definition here. So you see, this thing is still linear in Z, but then you will see that you don't have the linearity in U anymore. So you will have like a complex conjugation of linearity because on W and and because we say the linearity of the second argument is combined with this equation, but when you go, but when you switch U and alpha x plus beta w, alpha z plus beta w, so if you switch these two locations, you get the actual complex conjugation here, and so on the second register, you will actually get the alpha bar and the beta bar here. So that's the difference between real and the complex inner product. And here we have abstract version. So those derivations we're doing like C to the n, but you can also define the abstract version of complex inner product. Okay. So hopefully everyone understands. And that's the complex version of inner product. But I don't think we will see them anymore. Okay, it's just a small digression here, but but maybe you will find them useful in other courses, maybe signal processing, etc. Okay, just something you can remember. Okay, and then that's 5.4, and HR complex inner product. So let's go to what we actually want to talk about today. So 5.5 also normal state. Okay, and so this comes from this orthogonal thing. So back to 5.4. Remember we were talking about inner product space, and we can define this orthogonal this orthogonal property as inner product equals 0. Okay, and well, orthogonal is very nice, and so here we are going to introduce something very nice. Only when you have inner product, that is, you can find the basis that's also normal, basically. And what do we mean by bases are orthogonal? Orthonormal is that first all the basis element has known one, and also they are also orthogonal. All the basis elements are orthogonal to each other. Okay, so this is a thing that we can only define when we have a known and the concept of a known and orthogonal. Okay, and it's a generalization of the standard basis. Okay, and so in standard basis we think so there's a E1 and E2 that are very nice because those two vectors has known one and they are orthogonal to each other. Okay. And so we want to find more bases that are orthonormal. Okay. And we find out that we can define this, and then on 5.6 we will see a constructive way to find those orthonormal bases. Okay. And yeah, so we'll see that the orthonormal bases, because of the orthogonal, they have a lot of nice property, like you can find the projection easily and you can find the coordinate easily. Okay, so let's have a technical definition. So as we said, I guess before we talk about bases, we want to talk about orthogonal set. So we go one by one. Okay, so what do we mean by orthogonal set? So we just have a lot of vector, and if so every pair, so if n vector, then you have n choose 2 pair. So every pair, if they are orthogonal to each other, then we say it's an orthogonal set. Okay, this should be pretty obvious. So definition here, there are a lot of things to check. Although yeah. Yeah, for now you have n vector, then you should check n choose 2 of them. Although later, I guess we will not show, but actually you don't need to check that much. Okay, and let's give an example. This is a very brute force thing to check now. So you have a 3 vector, and you have 3 vector, and you want to see its orthogonal set. Then you need to check every pair is orthogonal. Okay. And then to check orthogonal, it's a straightforward calculation. So you check the inner product because we are in R3. So you check the inner product between those two, and so yeah, you can do the multiplication, addition, and see it's 0. Okay, so this one is easier. So this is 2 plus 1. 2 plus 1 minus 3 is 0. Okay. And then you check those two vectors are orthogonal, and it's 4 plus 1 minus 5 is 0. And then those two vectors are inner product is 0, then it's harder. I think it's 8 minus 5 minus 3, so it's also 0. Okay, so it's pretty straightforward. Okay. And okay, but orthogonal already tells us something. Okay. So orthogonal is a stronger property than inner product. So I guess the intuition is like this. So say you are in R2 and we have only 2 vectors. So inner product just means those two vectors. Orthogonal is stronger than linearly independent. Okay. So we think about 2 vectors in R2 and they are linear independent. That just means that they are not on the same line, right? So kind of they have a non-trivial angle here. But orthogonal means that the angle is not only they have angle, but the angle is 90 degrees. Okay. So orthogonal is a stronger property than linear independent. Okay. And okay, but we want the actual proof here, so let's go through the proof. And so let's assume this set is orthogonal, and we want to show it's linear independent. And remember in chapter 3, we want to show linear independency, then we want to check these equations. We want to say this is C1 V1 plus C2 V2 plus Cn Vn. We want to this summation equals 0, and only when all the C are 0. Okay. And then we have orthogonal, so we can do kind of this inner product thing. Okay. So then so let's assume this equals 0, then what we want to show is all those Ci are 0. Okay. And we show this by doing n different tests. So we pick all those V1 to Vn one by one, and inner product it with this linear combination. Okay. And okay, so Vj. uh, so say we pick the jth one, and we have a Vj inner product with all these things. And then now we use the linearity of inner product. So this is linear combination of all those inner products. So the inner product between Vj, V1, and Vj, V2, Vj, Vn. Okay. And here we can use orthogonal. Okay. So Vj product, inner product with some Vi is 0 for every. So Vj inner product with anything that's not Vj is 0 because the set is orthogonal. Okay, right. So this summation will just become Cj and the Vj inner product with itself. So that's a Vj non-square. Okay. Okay. So here we use a nice orthogonal property. And then we use another property that I didn't actually say, that also want this set to be non-zero. Okay. Because obviously you have something 0, then the set cannot be linearly independent. Okay. So those sets, this every element is non-zero. So this Vj square is non-zero. Okay. So Cj times something non-zero equals 0, then that means Cj equals 0. Okay. And that's what you do for Vj, but you can pick j for everything from 1 to n. So actually all those Cj equals 0. Okay. So Cj equals 0 for all j. And yeah, then that's the definition of linear independent. So this equals 0, then all the C equals 0. So this is linear independent. Okay. So orthogonal set is linear independent. Okay. And then we have defined orthonormal set, and it's just an orthogonal set, and every vector inside has a unit length. Okay, and so we have well, the standard basis example, it should be pretty clear. So these E1, E2, E3, they are orthogonal to each other because when you take inner product, then you are just summing over 0, 0, 0. Because 1 only hits 0 and 0 only hits 1, etc. So they are orthogonal to each other, and those are also normalized vectors. Those are also unit vector because they are no obviously equal to this 1. So 1 square taking square root is still 1. Yeah. So this is also normal set. Yeah. And yeah, you see that we can probably see here. So you get if you have an orthogonal set, it's pretty easy to get an orthonormal set because you just normalize each vector. So you just go like maybe right here. So if you have an orthogonal set, and then you just go V1 to V1 divided by norm V1, then you will get a unit vector, and yeah, and then you get also normal set. Okay, and yeah. So yeah, as we say here. Oh, yeah, I'm jumping ahead. So I guess I don't actually need this here. Sorry. Yeah, so I guess we write the two things in a more compact expression. So we say that our set is orthonormal if they are orthogonal to each other and have norm 1. So we can have the orthogonal to each other and norm 1 by just writing down all pairwise inner product. So we say pairwise inner product equal to this delta ij, which just means I equal to 1 when I equal to j, and 0 when I not equal to j. So 1 is they being normalized. So every vector inner product with itself will have equal to 1, and 0 is orthogonal 1. So it means pairwise. So it means that if these are two different vectors, then inner product equals 0. Okay. So this is normal and orthogonal. Okay. And just how I said. So every orthogonal set, then given orthogonal set, then you can find the corresponding orthonormal set by just normalizing everything. So you just divide every vector by its norm. Okay. So now every vector has norm 1, and you can easily check that by the linearity of inner product. So if your inner product is 0, then you divide by this norm, then inner product is still 0. Okay. Okay, and then let's see how this goes. So we have our orthogonal set before, so this 1, 1, 1, 2, 1, minus 3, and 4, minus 5, 1. Okay, and it is orthogonal, and then we say we can normalize each one of them to form an orthonormal set. And so known of this is square root 3, and it's square root 14, and square root 45. Okay. So yeah, so now this is also normal set from the orthogonal set that we were given. Okay. And okay, I guess so far any question? This is basically only definition now. We have defined the orthonormal set of vectors. So it's a vectors that well, orthogonal and normal. And orthogonal means inner product between different vectors are 0, and normal means each one of them has known 1. Okay. And anyway, then and then we can now talk about also normal basis. Okay, so we have this also normal set. Okay, so we are talking about this in real way. Okay, and we have also normal set, and then by the theorem we just showed, we say orthogonal is stronger than linear independence. Okay, so this set is also linear independent. Okay, and if we have a bunch of things that are linear independent, and if they span something, then it's a basis. Okay, so what does it span? Well, it span whatever thing they span. Okay, so anyway, so those casings will be a basis for this span. Okay, okay. So orthonormal basis is basically a basis that's also normal. Okay, so it's a stronger requirement of a basis. Okay, so yeah. You have a basis for something, and every vector inside you have a known one, and they are orthogonal to each other, then it's also no basis. Okay. And okay, and now okay, so before was just a definition, and now we see why we like orthonormal basis. Because orthonormal basis let you find the coefficients easily. Okay, so not coefficient, the coordinate. Okay, and yeah. So remember when we talk about basis, we always want to find those CJ, right? So given a basis, we say basis is nice because we can decompose anything inside your vector space as is a linear combination of basis element. And I think we have we do this in chapter 4, and we have a very pretty painful calculation to see how we change the coordinate between different bases, and to find this linear combination. Oh, actually, yeah. It's chapter 3, but anyway. So we had some calculation in Rn to see how to find the coefficient for different bases. Okay, and but if you have also no basis, then those Cj coefficients they have or Ci, so they have a very easy definition or easy calculation. By it's just the inner product of your vector with this corresponding basis. Okay, so yeah, so if you have orthonormal basis, then this linear combination coefficient is just this projection onto your orthonormal of your basis element. Okay, so it's very nice. It's kind of you can just back to our orthonormal basis example. This E1, E2, E3. So I guess that's a little too trivial, but yeah. Yeah, so like you want to find your element as a linear combination E1, E2, E3, then it's pretty clear that your x equal to x1, x2, x3. And the coefficient will be just x1, and that's the inner product of E1 with your thing, and the coefficient on E2 will be the x2, that's the inner product of E2 with your x, and the coefficient on x3 will be x3. Sorry, coefficient on E3 will be the x3, and that's the inner product of E3 and your x vector. Okay. And then that kind of a trivial thing, we say that it can be generalized to arbitrary inner product space. And we have some proof here. Yeah. And the proof starts from, well, your V has this unique decomposition just because your set of U is still a basis. And so we know your V is a linear combination, and then we just take an inner product of your V with some Ui here. Okay. And so what will happen? So your V can be written as this unique linear combination, and this is linear, and our inner product is linear, so we can pick summation coefficient outside. Okay. This is using the linearity of inner product. And so this thing is summation Cj. Why do I even? I'm not sure why I switch I and J here, but yeah, I should just have a Ji here. But anyway, they are the same. Okay, so we have summation Cj Uj Ui inner product, and Uj Ui inner product, because this is also normal set. We say this is delta ij, and basically this is non-zero only when I equal to j. Okay. So non-zero only when I equal to j, and so the summation, the only thing useful is when j equal to I, and okay, and so you only pick out. So when j equal to I, this is equal to 1, and they get ci, and when j not equal to I, those are all 0. So you just get Ci here. Okay? Yeah. So to find these linear coefficients for or the coordinates for orthonormal basis is much easier. You just take the inner product of your vector with the corresponding basis element. Okay. And okay, so most things make you think that the orthonormal basis kind of look like the standard basis. So also, if you write things into coordinate of your orthonormal basis, okay, so you have some U and a V. So U have coordinate AI, and V has coordinate BI. Okay, in terms of this. UI basis, and then the inner product between U and V will be kind of like in Rn, so it will be summation. It will be just the summation, this coordinate AI times coordinate BI together. Okay, and yeah, so you see these orthonormal bases really behave like the standard basis in Rn, where yeah, and so we have an example proof here. Excuse me. So proof here is once again just use the linearity of inner product. Okay, so I think this is okay. I guess yeah, why not? Although this is not very important. So we use the V and UI inner product equal to BI that we already proved, and so U inner product is V is is a little annoying. But anyway, so U inner product is V, and so we break U into this coordinate linear combination of coordinate, and then we use the linearity of the inner product. Okay, so once again, this is summation AI and UI inner product with V. And so here, then we can do. So here we can just use this thing to break the linearity on V again. But then we cheat a little bit, so we say this thing or this thing. That's from the previous calculation. Okay, and anyway, it's very similar. So you can break the linearity here. That's the previous calculation, and we see that this is BI. Okay. So basically, you just write this in here. Okay. So I keep going back and forth between this, but so here you can also just say this is, you can use the linearity on both sides and you just say U and the V inner product equal to this sum I, AI, UI inner product with sum J, BJ, UJ. And this is just sum ij, ai, bj, and ui, uj. And you have a delta function, and we'll turn this sum ij equal to sum I. Okay. It's a little more symmetric proof. Okay. Question? I guess we have 2 minutes, but let's have this first. And also, so one more thing. So we have inner product on also normal basis coordinate look like this standard basis coordinate y. And also the norm also, so this is corollary. So the norm can also be defined nicely. So if you have you have once again a vector written as this coordinate in your orthonormal basis, then the length square of your vector will be just this coordinate square summing together. And that's basically this thing with A equal to B, okay? Or A equal to B equal to C. Oh, where am I? Sorry. Yeah. And yeah, so norm square is inner product with yourself, so some CI square and CI square. Okay. Any question? If no question, then we can take a break a little earlier. So we'll come back in 10 minutes. Okay.
助教的解释没办法说服我。
哦，好。
是这一题。因为题目没有任何关于 x 的叙述，所以它不用是 r 的话，它根本不会 span 出 Rn 嘛。但助教给 true。
助教给 true， 对，对，这个是我们讲没有那边，等下，所以你是写 true 然后被打错了吗？
我写 false。然后就被换掉了。
可是你写 false， 你的解，我可以看你的答案吗？你的解答。
看不出来。
不是 false， 我们要求要解释吗？你解释的部分呢？
就这样。如果它是 C 的话，它就 span 出 C。
哦 ，OK， 那你这个算对，那这个我想想看要怎么讲，我要怎么跟助教讲？所以你对你这个我们有算对，但是助教没有对，因为这一题是比较奇怪，我们没有讲很清楚它在里面。OK， 你说 C， 好，那样的话，我想想看，你的学号是多少？我要怎么跟助教讲？对啊，应该是我要跟助教讲了，还是你直接跟，我直接。
直接从这封回复，这是主角回复系。
还是你直接回复，然后 CC 我，然后对你 CC 我，然后我就回个信说我同意这样子就好。
好，谢老师。
这是在哪里？课本上的，其实我之后会试着重申一次，希望会比较容易懂。但是课本上证明我记得还可以吧，所以所以等一下我要回想一下，现在什么东西什么东西，我们要证什么？哦，这个是我有试着证的那个。我现在思考这个 y 跟 z 是什么东西。所以我们是怎样linear independence已经证完了吗？这样子的话，所以我 x 跟 x q， 然后我 basis for x， 然后 basis for x q， 然后我是 element of， 我们现在是在证linear independence， 是不是？对，我要算是 basis， 然后我自己的课本好像是对，我要说它是linear independent， 然后我设了这个 coefficient， 然后y 是前面的东西，然后 z 是后面的东西。OK， 所以那它有这个样的东西，所以它先证 y 是负 z 嘛，所以 y 跟 z 是这样 ，y 是 z 再乘以 coefficient， 所以基本上 y 是一个。对 OK， 所以这里其实有4个东西要证嘛。它是说 element of x 跟 x 的 intersection with x q， 所以它说 y 在 x 里面，然后 y 也在 x q 里面，然后 z 在 x 里面的 z 也在 x q 里面，所以这有4件，这其实是讲了4件事情。对 y 为什么在 x q 里面？因为这个东西，原 z 在对原 z 在 x q 里面嘛。然后 x q 是 subspace， 所以 x q 有那个 closure under 这个乘以符号的东西。对，所以 y 在 x q 里面，然后 z 在 x 里面是一样的说法，原 z 是负 y， 所以 z 在 x q 里面。对。我觉得这个，我觉得我们讲完，我说诺贝其实这个会好证很多，所以我打算后面再重申一次。不知道，目前打算就是看一下进度，就是进度对的话，礼拜三我们会重申一次。这好像比较难。所以怎样？等下我先看一下这题在说什么。我认个 R， 然后我 basis， 然后就它是一个 basis， 我记得讲的好的，但是好吧，所以你讲的怎样？color space of A 的 rank， 不是啊 ，color space 这句话就，不是它是个 space 没有 rank，matrix 上 rank， 你要说 dimension 是 R，color space 的 dimension 是 R 是没错嘛，我们之前有证过这个，对。等一下，为什么？等一下，首先你写的有点奇怪，是为什么叫 rank R of A？ 你要是说 rank of A 吗？你就你讲的是 dimension，OK， 对 dimension， 对，这些东西的 dimension 全部都是 R， 那是没错的。 证得出来。好像应该证明女生的可以吧？我想想看，所以，这个东西的dimension是 r， 然后这里有 r 个东西，然后的确是你证出今天女生的话就结束。但我记得这样好像走过去了吧？我想想看。这它是一面这样的，这样。我一直看不到，我觉得你是不是可以说个 C 是在 null space 里面？就是 C 可能会在什么东西的 null space 里面吗？就是 C1、C2、C2的那个，那这样合理吗？你可以想一下，C 是在 AT 的 null 是不是？在这里。一样题目，好，等一下我在想这个，我一时忘记答案。对，好吧，对，这个我等一下再回答。就是它对啊，是小岁之后，那就是这个东西就要在这个东西嘛。管你好正常，比如说是这个，就是没有啊，如果 space 本来就是这个subspace 嘛，所以的确这一题就是说，只能说它在它里面。Hello. Okay. Let's back to our orthogonality. So yeah, so we see that orthonormal bases are really nice. It has orthonormal basis has a lot of structure. It acts quite like the standard basis, where its coordinate tell us a lot of things. So you can find the coordinate nicely. So you just take the inner product of your vector with your orthonormal basis. You can find the coordinate. And also, if you want to find the inner product of two vectors, then you just take the coordinate of those coordinate on your orthonormal basis. Okay? And this also means the non-square is coordinate square something together. Okay, and let's see an example. So we have orthonormal basis. That's kind of that's a little tilted. So I think we can draw geometry. So this is a basis of R2. So standard basis of R2 is like this x and y basis. So standard basis is a unit vector on x and y. And we are saying we can rotate things a little bit and get this other orthonormal basis as x plus y and x minus y. So it's a 45-degree thing. Okay, so you have u1 here and u2 here, and they are orthogonal to each other, and they are normalized to 1. And this is orthonormal basis, and it's basically the standard basis rotated by 45 degree, and it has a lot of nice property like standard basis. Okay. And so for example, so we have whatever vector x1, x2 inside the plane, and we say the coordinate of this x on our u1, u2 is for c1 is x transpose inner product with your u1, and that will be okay. Sorry, not x transpose inner product. So x inner product with u1, and that's x1 times 1 over square root 2 plus x2 times 1 over square root 2. So it's 1 over square root 2 x1 plus x2. And the coordinate on 2 will be x1 minus x2 takes 1 over square root 2. Okay? And so the coordinate will be like, so I was saying we have some x here with x1, x2, and then your coordinate here and the coordinate here can be calculated by the inner product. I guess this thing is not obvious from the geometry. Not too obvious from geometry, but you can take the inner product to find the coordinate here and here. So the coordinate C1 and the coordinate C2. Okay. And then we add it back to check that things are actually correct. So we think x is C1 U1 plus C2 U2, so kind of transform back to the standard basis. And so it's 1 over square root 2 x1 plus x2 u1 plus 1 over square root 2 x1 minus x2 u2. And yeah, and so you can kind of calculate this back. And so on the first coordinate, this will be, so if we transform this back to standard basis, because why not? So this times u1, u2, and so on. So this is 1 over 2, and x1 plus x2, x1 plus x2, plus 1 over 2, and x1 minus x2, and minus x1 plus x2. And so you add those together, you find out the first coordinate go back to x1, the second coordinate go back to x2. Okay, so that's x, and so that's the coefficient in u1 and u2, and then we know and see that the non-square is still the correct thing, and the non-square is x1 plus x2 square root 2 square, and x1 minus x2 square root 2 square. And yeah, so both of them have x1 squared plus x2 squared, and let's go to here. And the cross term is plus x1 x2, and it is minus x1 x2, and it's 0. Okay, so here is the example to show that orthonormal basis actually do what we think it do. Okay, okay, and then we can then we go to another concept that's things like not related to the orthonormal basis, but quite actually do. So these orthogonal matrices are basically matrices that transform between orthonormal bases. Okay, so kind of like we think about how we change from these standard basis to our U1, U2 basis, and they will be done by orthogonal matrices. Although I don't think we will do too much proof here. But anyway, so the definition of orthogonal matrix is a matrix. So it's first is a square matrix. So it's a n by n here, although we didn't highlight. So it's a n by n matrix, and you need all the column vectors from a orthonormal set. Okay, so basically this will be a transfer matrix from a standard basis to some orthonormal basis. And so let's write down a little bit. So once again, so we think this matrix Q has columns. So it's a column. Let's write Q. So it's column. So Q1 column, Q2 column, to Qn column. So we are saying all those column vectors, they are also normal to each other. So they need to all have norm 1, and they need to be all orthogonal to each other. And so if Q is this kind of matrix, then we call it orthogonal matrix. Okay. And then very soon we can have a theorem. So orthogonal matrix also says so you can also define in this way. So we define it in terms of every column is the columns are orthonormal set, and you can also show that if that's true, then that's if only if Q transpose times Q equals identity. Okay. And that means Q inverse is Q transpose. Okay. And this is basically from the the proof is basically you just take this definition and you see that you calculate Q transpose Q, you will get a whole bunch of inner product between the column vector, and that give you identity matrix. So maybe get this way, and let's still draw a picture. Okay. So you just think about what's Q transpose Q, and you have Q1 transpose 0, and Q2 transpose 0 like this, Q1 transpose 0. And then you have Q here, so Q1, Q2, these columns together, and then you see that QTQ, then every element here is actually like a row here in a product with a column here. Okay. So like the ij's element of Q transpose Q will just be the i's column of Q inner product with the j's column with Q, and we know that's delta ij. So so you know that when I not equal to j, then those inner product all equal to 0 because column of Q are orthogonal to each other. And on the diagonal, then you have column of Q inner product with itself, and those should all equal to 1 because the columns are normalized. Okay, so this is just direct calculation, and you see that basically by definition, this thing will equal to the identity matrix. All the diagonal equals 0 because of orthogonal, and all the diagonal equal to 1 because of normalization. Okay. And yeah, so we see that if Q is orthogonal, then QTQ equal to 1, and so QT equal to Q minus 1. And so now we have a bit interesting thing we can say. Let's see what I want to say. Okay, so yeah, so let's say QTQ equal to 1, and QQT also equal to 1. Right? Not 1, identity. And also we are talking about so this is n by n matrix. So we think about those columns in Rn, and we have n of them. And because they are orthogonal to each other, we know they are linearly independent. So actually, these columns are orthogonal basis for Rn. So another thing we can say is Q1, Q2, to Qn is a basis because there are n of them, and they are linearly independent. So they are also actually they are already also normal. So but they are already orthonormal because we say they are orthonormal, so they are orthonormal bases for Rn. Okay, that's something. And okay, and back here, so we're keeping back and forth. Okay, and QTQ also equal to identity, right? And so here we can see funny thing. Oh, maybe there will be homework, but anyway, I already talked about this. And we know QTT equal to Q, right? And so this thing is Q transpose. And so this means that QT is also orthogonal. Okay. So QT is also orthogonal. QT is also orthogonal, and this means that actually the rows of Q are also orthogonal basis for R. Just have a similar argument here, because the columns of Qt equal to rows of Q. Okay. And so that's right here, and this means rows of Q or basis for Rn. Okay, but yeah, that's a lot of digression. And let's back to just having an example of orthogonal matrix. Okay, and orthogonal matrix is this. So in R2 is this rotation matrix. So we have cosine theta, sin theta, minus sin theta, cosine theta. And so let's first check that this is actually orthogonal. So we want all the column vectors are orthonormal to each other. Okay, so so column vector Q1, Q2, so Q1 is this thing and Q2 is this thing. And so the norm square of Q1 is cosine square plus sine square equal to 1. Norm square of Q2 is sine square plus cosine square equal to 1. And the inner product is minus cosine theta sin theta plus cosine theta sin theta and equal to 0. Okay, so this is orthogonal matrix. And then we check our theorem is actually true. Okay, so if we have Qt, then so you transpose this thing, then you just move this minus sign to here. So cosine theta minus sin theta, cosine theta. And then you multiply those two things, and you see that our calculation was actually correct. So this element is cosine theta plus sin theta. And this 0 is cosine theta, sin theta minus sin theta, cosine theta. This 0 is cosine theta, sin theta minus cosine theta, sin theta. And this 1 is sin theta plus cosine theta. Okay, so yeah, so our theorem is correct, and QTQ equal to 1. Or actually we check a different thing. We check QQT equal to 1. Okay, that's a bit funny. So we actually check this equation instead of this equation. Yeah. And anyway, and this matrix is actually kind of nice. You should kind of remember it because it has a very geometric interpretation in R2. So it's a rotation matrix. So it rotates. So you see all the theta here. So theta is actually angle here. It's an angle that this matrix rotates. And so what this matrix do is it will rotate vector in R2 by angle theta like this. So rotate with respect to the original. Okay. So you apply Q on some vector x, then you will go to this theta angle rotation. And Q minus 1 will inverse what Q do and go back to this minus theta. So you have a vector y here and Q minus 1, and y will rotate the other direction by theta. Okay. So yeah, but the geometric. So this is example of this rotation orthogonal matrix, and so in general, all the rotation is all the orthogonal matrices are kind of like rotation, and they have the nice property that they basically preserve the geometry on your inner product space. So that means that the inner product is unchanged because you can kind of feel here. So if you rotate every plane, the whole plane, then a shape will not get distorted, right? So we have geometric interpretation here. So say you have some triangle here, right? Say you have some triangle here, and then you rotate every point with your cube, and then you still have a triangle here. So you have a triangle. Let's draw something that's more like a geometry. Okay. So what I want to say is these orthogonal matrices, they do basically rotations in high dimensional space, and they will preserve geometry. So say you have some triangle here, and you rotate the whole plane, then the triangle will go to a different place and orientation, but it's still a triangle. So you have all the angles still setting the same between the different edges. Okay. And in terms of algebra, then you can say this by seeing that all the inner product is getting preserved by orthogonal matrix. Okay. And this can be easily proved by just do a calculation. So inner product. I guess the orthogonal matrix. So this we are kind of back to not totally general. Wait. Let's see. Multiplied by a matrix. We are defining okay. Here is a bit funny. I guess. Yeah. Okay. So here we have a bit of high level definition crisis here. Okay. So we're gonna be talking about abstract inner product space, but now anyway, now we are back to we are kind of back to Rn. So not thinking about this xy is coordinate in Rn. Actually, standard basis in Rn. Okay. So that's how we write the qx and qy. Okay. And yeah, so so here we actually need like xy in Rn. Xy the coordinate vector in Rn. Okay. And yeah, because we define Q as a matrix, right? So let's think about those xy as standard basis coordination in Rn, and then you apply Q by multiplying Q on the coordinate of standard basis. And yeah, so that's Qx, Qy, and because now we are doing all the calculation in standard basis, and so the Qx, Qy inner product is just well, standard basis inner product is Qx transpose times Qy. Okay, and so then now we do, so now everything is matrix, and then we do standard basis so we do the usual matrix modification. So we think X as a matrix, Q as a matrix, and you do transpose, then it's X transpose, Q transpose. And finally, we use the property of Q being orthogonal matrix, and we show that QTQ equal to identity. Okay. So QQ is identity matrix, so this is just XTY, and that's X inner product with Y. Okay. And yeah. And if you pick y equal to x, then you also see that Q doesn't change the length of your vector. So x inner product with x will equal to qx inner product with qx. So qx non square equal to qx. Okay. Yeah. So you see that you transform your vector by, or you multiply your vector Rn vector by orthogonal matrix, then the angle between them doesn't change and the length of your vector doesn't change. Okay. Yeah. And so here is a bit of a summary about this orthogonal matrix. I guess we didn't go abstract here, so we really want, we can define an abstract version of orthogonal matrix, but let's just know that it exists, so we don't go to detail here. But anyway, so we have Rn version here, so here is a bit confusing. So we have been talking about abstract version, but this orthogonal is defined on Rn. And so defined Rn, then our orthogonal matrix is a very specific form. It's n by n. Is an n by n matrix. It has n squared numbers, and once again, remember we define this matrix as just this n squared number listing here, and each column need to be orthonormal to each other. The columns need to be orthonormal to each other, and yeah, and so that's the definition of orthogonal, and we show that that means QTQ equal to identity, and that means QT equal to Q minus 1. And you can also show that you apply those Rn vectors x and y, then this Q will preserve inner product, and that will also means it preserve length. Okay. And okay, and then we see one more thing about what's good about orthonormal basis. And that's that if you have an orthonormal basis, then you can do the least square calculation easily. Okay. And yeah. So recall we solve least square by saying that, so you want to solve x and b and you can't. So instead you multiply AT on both sides. So you want to solve ATAX equal to ATB. Okay. And also, oh, here is something we forgot to change again. So this is C of A by our notation. Okay. And also we have the projection vector. So if the answer is x hat, and then we see this C of this P is the projection. The P will be the projection of B onto your column space. Okay. Okay. And we say that the least square problem is easy if the columns of A form an orthonormal set. Okay. And well. So let's kind of draw this idea here. So we have A, and we have columns of A. Okay. And so we are saying so want to solve A is equal to B, and it's hard usually when M is much larger than N. So we have those long columns. But anyway, then here we say the columns of A form an orthonormal set. Then it will be very easy to solve your least square problem. Okay. And well, what would be easy then? Then first of all, it's orthogonal to each other, so it's linear independent to each other. And we already know that if they are linear independent to each other, so we show this with a lot of effort, but we show that. If they are linear independent, then ATA will be full rank, and ATA is inverse. Okay. But actually, if they are orthonormal, then ATA is even stronger property than non-singular. Okay. And if they are orthonormal, okay. So if they are orthonormal, actually ATA equal to identity. So here, this is a bit confusing. So ATA equal to identity doesn't mean this is, I guess, a bit of a notation thing. So let's write this down. Okay. So remember, ATA is n by n, and with n larger than n. usually, and bigger than n. Yeah, let's assume n bigger than n, although not necessarily. But let's talk about general. Okay, so n bigger than n, and we have those n different column vectors that in Rn. So we have those vectors. So I guess let's call this A1, A2 to AN. So the AI they are in Rn, and then you have those rows. So in AT, then you have this A1T, A2T, ANT, right? Okay. So and this is n by n matrix, and its identity here. Okay. And okay, so what's confusing here? What's confusing is m not equal to n. Okay. Although it might not be confusing to you, but but let's try to make you confused and show you why it's okay. Okay. So as ATA equal identity, so it looks a bit like AT is A inverse, but that's not quite true. So because first of all, we only define A inverse on n by n matrix, remember, and also this is different because ATA equal identity, but AAT will not equal to identity. Okay, AAT is not equal to identity because AAT will be an n by n matrix, and well, that will not be identity. And yeah, so here the thing is that we have n vector here, n vectors in Rn that are orthonormal to each other, and well, by orthogonal they are also linearly independent to each other, but they are still not the basis for Rn. Okay. So if you want A to be invertible, then you want all the columns to be actually a basis for Rn. Well, they are not a basis for Rn because they are linearly independent, but you just don't have enough of them. So if you want the actual basis for Rn, then you need to find the other vectors here. Okay, and yeah, so this is not a basis for Rn, but still they are orthonormal to each other, and so you do this ATA, then you find out that they still span. So they are not basis for 4Rn, but they are basis for n-dimensional subbasis for Rn. That's whatever basis they span, and that's why you take this ATA, then you go to identity. It kind of says that in the n-dimensional basis they span, they are very nice basis. They are also no basis. Okay. And yeah, and anyway, so that's a bit renting is orthonormal column A. But back to solving least square. So what do we want to solve least square? We want to solve this equation, ATAX equal to ATB. But now with ATA equal to identity, and that means X just equal to ATB. So we basically can skip all the taking inverse of ATA step, and we just say X hat equal to ATB. Okay. So that's about least square. Any question? Okay, if no question, then let's go to the part where. Okay, then now let's go to the interesting part. More interesting part. This is the thing that we just updated this morning. So let's talk about more geometry by this orthonormal set. Okay. So we have been saying that so orthonormal basis is really nice. Remember, let's go jump back a little bit. Oh, actually, let's just stay here. Okay. Yeah. So orthonormal basis is very nice because so if you have some subspace S here, and you have orthonormal basis for it, and then you can find the projection onto the subspace very easily. Okay. So this is kind of extension of what we do here, because remember when we talk about least square problem, we were like trying to say we want to project onto the column space of our A, and it was very painful, and we need to kind of try to have the ATA inverse, etc. And and then we see that if you all have orthonormal basis, then this projection onto your space is not too hard. And we see that you can just do so if you have whatever state here, whatever vector here, and you want a projection onto your your subspace S, then you just take the those so you take the projection coefficients Ci equal to X inner product with your basis element Xi. Okay. So I guess we should draw a little bit more here. So we're thinking we have some basis, orthonormal basis here, x1, x2, they are orthogonal and they are normal. Okay, and so we want to find the projection of P onto the space. Then you find the projection of P onto all the basis elements. So you take this Ci. Okay. So remember, if this X is 4 orthonormal basis or 4 over the whole space V, then this is the scalar projection of X onto each Xi. Okay. So you have this Ci is the inner product of X equal to Xi, and yeah. And so you have those Ci, and then you just say your projection vector P is some Ci Xi, where Ci is a scalar projection, and Xi is your basis here. Okay. I guess, okay, so I want to say something funny here. So I guess this is kind of an extension of what we had before. So before we have saying like, so say, if you extend this thing to be a full whole basis, right? So you have x1, x2, dot 2. Okay, let's say this k here, so it's nicer. So let's say the dimension of S equal to k and the dimension of V equal to n. And you can kind of think that, okay, so it's actually always possible, but we didn't prove. But you can always have orthonormal basis for S. So you have x1, x2 to xk, and so this is orthonormal basis for S, and then the complement of S. Then you have you can have xk plus 1 to all xn, and this is On basis for V. Okay, so we haven't proved this yet, but it's actually always possible to find orthonormal basis like this, and so this part will be orthonormal basis for S, and this part will be orthonormal basis for S dual. Okay, and so what we are saying here, we are saying, so now this is the basis for V, so we are saying every X can be written as a linear combination of those things with a coefficient like this, right? This is the first thing we say about orthonormal basis. We say the coordinate in this x1 to xn is just X inner product with every with xi, and okay, so X should be okay. So in terms of this basis, X will be equal to some I from 1 to n. Okay. Okay. So now this thing is k, because I would like it to be k. Okay. So X in terms of this basis is some I to n Ci xi. Okay. So because it is a basis for the whole space V, and we can say X is some coefficient and elements. And so what is P? We say P is we truncate the summation because because the basis for S only have the first K elements. So we say we truncate the summation and we taking only the sum x1 to xk part, and then that will be the projection vector onto the x projection onto S. Okay. Okay. So that's the idea of the theorem. But let's prove this without actually having the extra part. Okay. So let's prove this without the extra part. And anyway, want to say the projection vector, then we want to say the leftover part is orthogonal to P. So we want to say the other part, this thing is orthogonal to this part. And how we prove this without having the full basis is like this. Okay. And so we show that the leftover part, why do we, P minus X, oh, okay, yeah, so, okay, it's a bit funny, instead of X minus P, we have P minus X, but it's similar, okay. Anyway, we say the P minus X part is orthogonal to P, okay. And we want P minus X to be orthogonal to P, and we first show that P minus X is actually orthogonal to everything S. So we want to say it's orthogonal to every base element of S. Okay. And xi inner product with P minus X, then by linearity is xi inner product with P minus xi inner product with X. And then we see that P is, well, P is this series. Okay, it's keep going to N, so I guess I should really switch back X and yeah, I will change that later. But I should really switch N and X and then K, otherwise it's really annoying. Okay. And anyway, yeah, so it's a sum to this N, so this N is a dimension of S. Okay. And anyway, CJ and now you can use linearity on this thing. And anyway, and xi inner product with X as a definition is Ci. And now we have Cj xi inner product with Aj. But now we use xi aj are also normal to each other. And so the summation j is only have a non-trivial one when I equal j. And when I equal j, because this is normalized, so it's actually 1. So this is also Ci. So you have Ci minus Ci equals 0. Okay. And so actually say P minus X is orthogonal to, well, I have a U here. This is so funny. Okay. So now this is just wrong. So P minus X is orthogonal to every Xi here. Okay. And so basically we say P minus X is orthogonal to every basis element inside S, and it will be orthogonal to everything inside S, including this P. And now the second step. Yeah. So this P is wait. What do we show? Oh, okay. So yeah, so sorry, I'm saying our statement wrong. So we want to say P minus X is orthogonal to everything to S. So actually show more than is orthogonal to P. But anyway, yeah. So P minus S is in S dual means it's orthogonal to everything in S. And so everything in S can be written as a linear combination of our orthogonal bases. And we know that P minus X is, and so Y written as a linear combination of our bases. Then once again use the linearity of inner product. So it's an inner linear combination of inner product between our P minus X and basis element. But we already said that for every basis element, this inner product is 0. And yeah, so this is 0. Okay. And no question, then okay, now it's a bit funny. I don't think we can talk this in 10 minutes. But actually you have 5.6 here. So I guess the first is going to be about spoiler. So we have said that orthonormal basis is very nice because it holds this property. Like you can find the projection really nicely, you can find coefficient really nicely, you can calculate inner product nicely, you can calculate norm nicely. And then 5.6, we will talk about this Gram-Schmidt process that actually let you find the orthonormal basis. So you can find orthonormal basis from any basis, and actually you can find it from any set, and you can theoretically find orthonormal basis on any finite dimensional space. Okay, but let's go back a little bit. So I guess this should be on Wednesday, and okay, yeah. So we'll talk about this on Wednesday, and today let's just finish this checklist for 5.5. Okay, and yeah, we have said that orthonormal set is really nice, and well, first orthogonal. If you just have an orthogonal set, then orthogonal is stronger than linear independent, because linear independent basically means that everything kind of angles between them, and orthonormal means that your angle needs to be all 90 degrees to each other. Okay? And orthonormal set has a lot of properties. So for example, with the basis, then coordinate is the inner product between your vector with your basis element. Is very important. Okay, so maybe let's highlight this here. The coefficient equal to inner product with the coordinate equal to this thing, and also the inner product will be like the standard basis. Inner product will be like a standard basis inner product of coordinates. So okay, but it's hard to write, so that's not right here. Okay. And also then we have this orthogonal matrix that's kind of back to R, and we define orthogonal matrix as a matrix where all the columns are orthonormal to each other, and because just by counting the columns will form orthonormal basis for R. And we see that that's equivalent to QTQ equal to identity, and that will also mean QQT equal to identity. And orthogonal matrices are really nice because they are kind of a transformation between orthonormal bases, and those transformation will preserve inner product. The QTX, QTY inner product equal to Q equal to X inner product with Y, and QX norm will equal to X norm. And then we have in the orthonormal base, if you have an orthonormal set, then this square is easy. Okay? And yeah, because if ATA, so if a columns of A is orthonormal set, then ATA will equal to identity, then X just equal to ATB. And yeah. And then we see that if you have an orthonormal basis, then projection onto your subspace is easy, because you can kind of just calculate the coefficient onto, you can calculate the projection onto all the basis element here, and just sum over those projections, and it will be the projection of your X onto your space. Okay, and we have 4 more minutes, so I guess we can say really quickly about how to find the orthonormal basis. Although we'll do more more detailed explanation on Wednesday. So how do you find the orthonormal basis? Let's say we have some basis x1 to xn, okay, and okay, so we have some basis of our space here, and we to find the orthonormal basis. Then what we do is, well, we want to find this U1 to UK as an orthonormal basis, and so it has 3 things, right? So basically it needs to be normal, and it needs to be orthogonal, and also need to be a basis. So the span of those things you need to be span of those things. Okay. And so first we want so we contrast those one by one. We kind of add those one by one to make sure the span is the same. Okay. And so first, okay. Yeah. So we add those one by one to make sure each time we have the same span. So first we take x1 and want the basis for span of x1, and that's also normal to each other. And x1 is just itself, so there is no orthogonal requirement, and then you just normalize it by normalize x1 divided by normal x1. So the u1 will span x1. Have the same span of x1, and it's also normal set because it's just one of it and it's normalized. And then what you do in U2 is kind of this idea. Okay? So you already have the U1 here, right? And then you try to add x2 into this set. So you try to add x2 equal to this U1 span. So x2 is like here, okay? But x2 is not orthogonal to U1. So first thing you do is you find the orthogonal projection of x2 onto u1. So here u1 here and x2 here. So what you want is you want to get rid of the component of x2 that's like a same direction of u1, and you want to find the remaining one. Okay. You want so my drawing is bad here. Let's draw a little better. The idea is you have the u1 here as a little shorter. So then you want to decompose your x2 equal to this p. I guess it's a p1 here. Although I think I want to say p2. But anyway, you have p1 here as a projection of x2 onto this u1 direction. And then you have this orthogonal part remaining. And yeah. So you want to take this part like u2, okay? And so you take this part and you normalize it, it will be u2. And then, okay, so to find the projection of x2 onto u1, then that's the thing that we've been talking about. Because the coefficient is there's x2 inner product with u1, and yeah. And then it's in u1 direction, so it's times u1. And okay, so by the thing we just talked about here, this is 5.5.7, then you have the projection by calculating the inner product, and you subtract it out, then the remaining part will be orthogonal to your u1. Okay, so we find something that's orthogonal to u1, and this thing will will help you construct u2. Okay, and yeah, so detail we'll see next time. And so that's the idea. You find the orthogonal part of your x2 and you normalize it and you got u2. And then you keep going, and so now you have the span of x1, x2, the span of u1, u2, and you try to add x3 in by having a projection of x3 onto this x1, x2, and take the remaining part into u2, u3, and yeah. Then you go through everything and you will get your orthogonal basis. Okay, but we'll see this in more detail on Wednesday. Any question? Otherwise, I'll stop here for now. Okay. Okay, so see you on Wednesday.